Okay, so in this video we're going to pick up where we left off last time in section 7.5, and we're going to look at an example of finding work using Hooke's law. So Hooke's law is the force, what does it say? It says that the force F required to compress a string or stretch a spring is proportional to the distance d that the spring is compressed or stretched from its original length. That is, the force is equal to, and I already have it written here, K times D. So K is this constant of proportionality called the spring constant, and it depends on the specific spring, right? So if a spring is made out of a certain material, where it's thicker or maybe thinner, it will give a different spring constant, right? So what's going to be more helpful for us here is, remember, we're we're finding the work, so we need to take the integral of the force function. So let's rewrite this and say what Hooke's law is a function. What Hooke's law is a function is it says, okay, it's a function of x of the distance, right? I plug in different distances and it gives me different forces depending on what k is, right? So my force function here is kx, where x is that distance that we stretched the spring. Okay, so let's look at example 2 here. A force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 meters, and we want to find the work done in compressing the spring an additional 0.3 meters. Well, we know work is given by our formula, the integral from a to b of the force function. And in this equation, or I'm sorry, in this example though, we're not given the force function because we're not given that spring constant, right? But we're given enough information. We're given that the force of 30 newtons is when I compress the spring 0.3 meters, so I know the force at a certain distance, so I can use that to solve for k. Once I know k, then I'll have the force function, right? So we need to find k. So when I plug in 0.3 meters, in other words, when I stretch it when I compress it 0.3 meters, I know that my force is 30 newtons, all right? But what's my equation here? It's k times x. Well, what is x? X is how far I stretched it. That's what we plugged in, 0.3. So now I can solve this equation by dividing by 0.3, and that will give me 100 equals to k. So in other words, my force function for this problem is big F of x equals to 100x, because k we solved to get 100. Now that we have a force function, we're able to solve for work. So work is equal to the integral, and now we have to find a and b, where we start and finish. The question says, first we compress the spring 0.3 meters, and then we want to find the work done in compressing the spring an additional 0.3 meters. Right? So here we're starting at 0.3, and we're compressing it an additional 0.3, in other words, all the way to 0.6 meters. My force function is 100x dx. Now this just becomes a simple integral problem. So we get 50x squared, evaluated from 0.6 to 0.3, and if I solve that, I end up getting 13.5, and then my unit, in this case we were dealing with meters, so it's SI units, so it's joules. Not too bad. So in this example, and any of the Hooke's law problems where we're looking at springs, you're able to find a force function, right? And then you can just integrate it, and life is good. Unfortunately though, oftentimes, especially with these fluid problems we'll look at here in a second, we won't be able to find a force function, right? But we can think about it as increments of work. We can think about the total work as increments of work. So the total work is the summation of increments of work of the form delta W, right? Because remember, if we look at the second formula here, right, not the second formula, the first formula, we know that work is equal to adding up infinitely many of those areas, right, those rectangles, and remember those areas correspond to the work on each one of those little intervals, right? So if I determine what the work is on each one of those little intervals, and I add it all up, then I'll get the total work. That's the idea behind this increments of work. So we can think of that delta W sub I, or that delta W in this case, as, remember, it's the work done on that little interval. So I can think about it as the force done times how far it traveled, or the force done to move it times the distance, right? So in other words, that delta can go in each place, right? And the one that's going to be most helpful for us is thinking about that delta going with the force, right? And remember, delta F is just the force required to move whatever increment or whatever we're moving that small interval. So again, this is helpful for fluids and chains. Another thing that we're going to need here is that force is equal to weight, right? And weight is density times volume. So we need to realize that for those problems as well. Okay, so let's look at example 3 here. An open tank has the shape of an inverted circular cone. The tank is 12 meters high with a radius of 5 meters and is filled to a height of 9 meters. How much work is done in emptying the tank by pumping water over the top edge? And the water weighs 9,800 newtons per cubic meter. So first, let's draw a picture of what's going on here. So I'm going to draw my cone. Oops. And so we know the radius of this cone that's given in the problem. That radius is 5 meters. And we know the height of this cone is 12 meters. What else do we know? We also know that there's water inside of it. Oops. All the way up 9 meters high, right? So what does that mean? That means this extra distance right here from the water to the top of the cone is 3 meters, right? If the whole thing is 12. Okay, so what are we gonna do here? Let's consider the water to be divided into discs of thickness, we'll say delta Y, and radius, we'll call it R, and Y from the x-axis. So in other words, let's draw what I'm talking about. Let's draw this disc. We'll do it in green here. So what I'm saying is take a piece of this water here, or I'm taking the whole water, and I'm dividing it into a bunch of these discs, just like this. The radius of this disc, we're going to call R. The height that it is from the x-axis, we're going to call Y, because this is a vertical cone. And then the width of this disc is going to be delta Y. So to solve this problem, what are we going to do? To solve this problem, we will determine the work to push each disc of water out of the top of the cone, right? And again, this is the idea of this increments of work, because one increment of work is one, the work for one of those disks. Okay, so step one here. In order to find, well, actually, let's label a couple things. First, let's call delta W to be the work required to push each disk, put a line here, each disk out of the tank, right, the cone tank. And delta F would be the force required to push each disk out of the tank, right? So what we're going to do here is we're going to try to find that delta W, right? That's the whole point. That's what I said. To solve this problem, we need to find that delta W, and then we'll be able to integrate that delta W. So in order to find delta W, work, remember work, we need force. And if we go back up to our little equation here that I have in orange, remember delta W is delta force, or delta F times the distance x. So remember, this x doesn't necessarily mean the variable x, it just means the distance. Okay, so in order to find delta work, we need to find delta force. In order to find delta force, we have to find the volume, because volume will give us the force, right? So step one, find the volume of each disk. Okay, so if we zoom in on each disk there, notice that it is a cylinder, right? Each disk is a cylinder. Right? We know the volume of a cylinder in general is pi r squared h. So in this case, let's fill in what r squared and rh is. R squared is still r because we called our radius r. And our height now, what's the height of each one of those disks? Delta y. That's our volume. So now that we have volume, we can move to force, right? Because force is equal to the density times the volume, and we know the density of water given by the problem. So step two here, find the force. I'm just going to say for each disk, but when I'm saying that, I mean the force required to push that disk out of the top. Okay, so delta force is equal to the density times the volume, right? Okay, well, the density is given in the problem there. It says water weighs 9,800 newtons per cubic meter. So this is 9,800, and then I'm going to multiply that times the volume, which we just found to be pi r squared delta y. Right, so this is 9,800 pi r squared delta y. Okay, so we have to take a little pause here because what am I going to end up doing with that delta force? That delta force, I'm going to end up I'm going to multiply it times the distance to get delta work, and then I'm going to integrate it. So if I'm going to integrate it, that means that this delta y right here, put a different color, this delta y is my my variable of integration, right? Y is my variable. But that's an issue because if we look at that equation we have, r squared is not y, right? But we can find r squared in terms of y by looking at our tank, right? So what we have to do now is find r squared, or let's say just r, in terms of y. And the way we're going to do that again is by looking back at our tank. So if we look at our tank here and we look at vertical slices or vertical cross sections, notice we get a bunch of triangles, right? And so say we take one vertical slice right down the middle of our cone here. If we did that, we would get similar triangles, and I'll show you what I mean here. So this is a vertical cross section. Oops. I think that's 2 words. And so I would get my big vertical triangle. What's the height of this triangle? 12. I'm going to pull this down just so it's not in the middle of the paper. And what is the smaller side? Well, that's 5 because we know the radius is 5. And then now, if we look back up here, we have the other triangle that's inside of that is the triangle that's formed with the x-axis, or I'm sorry, the y-axis and our disk, our radius r. So I'll draw that triangle in green. Right, so in other words, I have this other triangle that's right here, right, and this what we call is our radius, and then the height here we called this y, right, because it's y units from the top. And this is helpful because now I can use similar triangles in order to find an equation for r in terms of y, right? So here now, let's go back to red because that's what we're looking at. So using similar triangles, what do we get? We get that 5 over 12 is equal to r over y. So now if we solve that, we end up getting that 5y, whoops, I'm gonna do that in red. 5y equals to 12r. So in other words, 5 over 12y equals to r. And then what do we need? We need r squared for our problem. So that means that r squared is equal to 25 over 144 y squared. So now we're going to take that and we're going to plug it into our delta f. Right? So now our delta f function is going to be 9800 pi. Instead of r squared, we write 25 over 144 y squared delta y. So now that our delta force is in terms of the variable y. If we simplify that, we get 30625 over 18 pi y squared delta y. So that is our delta f. So now that we have delta f, we're able to find delta w, our increment of work. So now what step are we at? 3. Find the work for each disk. Right? So remember, delta W is equal to, given by the formula that we talked about right up here at the top in orange, is delta F times the distance x. Right? So it's delta F times the distance that it has to travel. Right? That disk has to travel. So let's talk about what that distance that it has to travel is. Let's draw it with another color up here. Let's see here. I haven't used orange. So if I have this disk right here, I need to figure out, in order to find the distance for the distance that travels to figure out the work, I need to figure out the distance that the disk travels. In other words, I need to figure out this distance right here. Well, I know that this little distance down here is y. I know that the whole distance is 12, so this little piece right here is 12 minus y. So 12 minus y is the distance that each disk has to travel, so it's the distance that I need to use in my force function. Right? So here I get, in my work function. So here my force is 30625 over 18 pi y squared delta y, and then now I multiply that times the distance, which we said was 12 minus y. I'll use orange so we remember where it came from. So I'm going to end up integrating this delta w, so I should get all my y's together and get my constants out front. So in other words, I'm going to distribute this y here. So I get 30625 18 and then pi, and then I get 12y squared minus y cubed times delta y. So now I'm ready for step 4 to find the total work. The idea of this problem was we found the increment of work in the previous step, right? We found that delta w, and now we can integrate it to find the total work. So in order to find the total work, we're going to integrate that, but we need to have our limits of integration. Right? So I'm going to put a little bit of a blank because in between that because of our constants for what our delta w is. So what are we going to integrate this from? So if we look back up at our, sorry, this is glitching out on me. We look back up at our problem here. What pieces of remember, what are we plugging into the problem? We're plugging in y, right? That's what we're plugging into the integral. So y is the possible height of water that we're going to be having these discs at to push it out of the top, right? So what are the possible y values that we have for the heights of those discs? Well, those range from 0 to 9, right? Because that's the piece of the water that we're going to make into discs to push out the top. So my integral here goes from 0 to 9. And then now I fill out the rest, right? I get the 30625 over 18 pi because it's a constant. And now I get my 12y squared minus y cubed times my delta y, but that changes to a dy when I take the integral. Right, so now I get 30625 over 18 pi, and now I get 4 y cubed minus 1/4 y to the 4th, evaluated from 0 to 9. And when I multiply that all out, I end up getting 6,897,4.12. And I'll write approximately here. Which also is approximately 6.82. Whoops, and I should put my units. My units are joules here. Why? Because we were in meters and SI. Right, so 6.82 times 10 to the 6 joules. Okay. So the way these problems work when I'm dealing with fluids, just to rehash here, I'm going to find my volume first of each one of those little cross sections, those discs. Then I'll find the force for each one of those discs. Then I'll find the work for each one of those discs, and then I can integrate. Right, so it's a long problem. So let's look at one more here. This one's actually a little bit easier. So a rectangular prism with base 4 foot by 5 foot and height 4 foot is full of water. The water weighs 62.4 pounds per cubic foot, and the question is how much work is done in pumping water out over the top edge in order to empty A, half the tank, or B, all of the tank. So first let's draw our picture here. So this is our rectangular tank. It has a base of 4 feet by 5 feet, and then it has a height of 4 feet. Right, and it's completely full of water, so I'm not going to draw the water in there. So now we want to find the total number of work. So again, we're going to do this by increments of work. So step 1 is going to be just like before. Well, actually, let's write out what our variables are. Delta F, remember, is the force to push one. Whoops! Before I hop into that, we should draw what our little cross sections are. In the last part, they were discs. Now they're just going to be little rectangular prisms. Right. So here's what our little cross sections are. Right, and we're going to call this distance delta y. We're going to call this distance now for the distance from the top of the rectangle to the rectangle. We're going to call that y. Okay, so now, like I said, we're going to do the problems before that. We have our cross sections. For our delta F is the force to push one small rectangular, running out of room, prism to the top, and then again delta W is the work to push one rectangular prism to the top. Okay, so we've got our variables there. We know what we're looking at. So now let's find the volume, and then we'll find the force, and then we'll find the work. So step 1, we need to find the volume of each rectangular prism. So each rectangular prism is a rectangle, so volume is equal to length times width times height. So in our case, what is the length of each one of those? The length is going to be 5. The width is going to be 4. And then the height is going to be delta y. All right, so it's going to be 20 delta y. It's going to be our volume. So now step 2, we need to find our increment of force. So find I'm just going to again say find the force of each rectangular prism. And here's where this problem isn't quite as difficult as the last one. So remember, delta force is equal to the density times the volume, right? But what is density? Given by the problem, it's 62.4, and then the volume, which we just solved for, was 20 delta y. Right? So here I get 1248 delta y. So unlike in the previous problem, my delta force function doesn't even have a y in it, so it doesn't have a different variable that we have to do some fancy footwork to solve for. Okay, so now step 3 is finding our work. So in this case, I should probably say that we're doing part A. All right, so first we're looking at part A, which is emptying half the tank, right? Because that's gonna help us. So delta W here again is equal to our delta force times the distance that each one of those travels, right? Step 3 is finding the work of each rectangular prism, right? So delta F, we just solved for that. That was 1248 delta Y. And if we look at the problem, what's the distance that each one of those has to travel, each one of those prisms? And by design, by the way we set it up, we said that each has to travel Y, right? That's the distance out here to the left. So that's what goes there for distance. And so I get 1248 delta Y times Y. So let's put the Y here and then delta Y. So now step 4 is where we integrate to find the total work. Okay, so the hardest part here is determining our, I'm going to leave a little space for our constants, our limits of integration, right? In this case, we want to push half the tank out, right? So if we want to push half the tank out, what does that mean? That means that we, which portions are we moving? We're moving the portion from half the tank is 2 feet high, right? So we're moving the portion from 0 to 2, right? That's the water here. So from 0 to 2 would give us half the tank out of the top, right? So now we get 12, 4, 8, y, and then that delta y changes to dy, and we integrate. So I get 624 y squared evaluated from 0 to 2, which gives me 2496. This time my unit is foot-pounds because I'm dealing with US units, right? B. Okay, so now the question is how much work to pump out all the water out of all of the tank, right, to get all the water out. So one would think, right, for part B, that I could just take part A, which is, whoops, sorry guys, which is how much work is required to push half the tank, multiply it by 2, that gives me the whole tank. But that's actually not the case here. So we have to be a little bit more careful. So everything is still the same up until step 4 when I put those limits of integration on, because that's where the depth of the water that we're pushing out changes. So step 1 through step 3 are the same. But now step 4 is different. And it's different again because we're going to have to change those limits of integration because of how much water we're pumping out at the top. So again, this is find the total work. So now, leave my space here, it's 12, 4, 8, and now I'm going to go from 0 to 4, right? Because the water is, we want to pump the water out from the bottom all the way to the top, right? So now I get the y dy, I integrate this, which gives me 624 y squared from 0 to 4, which gives me an answer of 9984 foot-pounds. So again, notice that we don't multiply part A, or the amount of work that it takes to push half the water out, by 2, because 2,496, the answer for part A, times 2 is not 9,000. Right? Okay, and there's some relevant textbook exercises for you. Thanks for listening.